Okay, so let's understand how to find the important features in logistic regression. So let's assume we have D features, F1, F2, so on, Fj, right? So on, so forth, Fd. So you have D features, the general feature is called Fj. And when you compute your weight vector, the optimal weight vector, you get weights corresponding to each feature, right? You get Fj, so on, so forth. Sorry, you get each of the weights corresponding to the feature. So W1 corresponds to feature 1, W2 corresponds to feature 2, WF corresponds to, sorry, WJ I should say, sorry, that's a typo there. So WJ corresponds to Fj and WD corresponds to FD. So this is how we have our feature weights. Now a big assumption, the assumption we are making, let's assume that all features are independent. Let's assume if this is true, if all features are independent, right? This is the same assumption that we had in naive Bayes, right? Remember? Because remember, what is logistic regression from a probability standpoint? From a probability standpoint, logistic regression is nothing but Gaussian naive Bayes plus Bernoulli distribution on class labels, right? So if all features are independent, if all the features are independent, then there is a very interesting conclusion we can come to, right? So the interesting conclusion we can come to is we can get feature importance. We can get feature importance. We can get feature importance using WJs. If this is true, if this is not true, everything that I'm saying may not always hold true, right? So if all your features are independent, if it is so, in the real world, it's not easy for that to really happen. If it is so, then we can get feature importance. I can tell you which feature is more important, right, in determining my class label by just looking at the weight, just by looking at the weight vector without doing anything else, right? So if you recall, in k nearest neighbor, we could find the most important features. We could get feature importance. We could get feature importance not from the model, but by using additional techniques like forward feature selection, right? We saw this when we learned k nearest neighbor, right? So we learned forward feature selection method to determine which features are more important, because k nearest neighbor inherently doesn't tell us which features are important. Whereas in naive Bayes, if you recall, in naive Bayes, we could tell which feature is more important using probability of xi given y equals to +1. By using these conditional probabilities, we could get feature importance. I could tell you which features or which words were more important, right? So we could get the features which are important to determine positive label, which are important to determine the class label, right? We could do that. We could do it using conditional probabilities in naive Bayes. What about logistic regression? Right? In k nearest neighbor, there is no inherent technique, and hence we use the forward feature selection. Remember, forward feature selection is algorithm independent. I can apply forward feature selection on naive Bayes and also logistic regression. But in naive Bayes, these conditional probabilities got me some intuition on which features are important. In logistic regression, I can take WJs to determine. I can use WJs to determine feature importance. To determine feature importance. I'll just call Fi for feature importance, right? Now, how do we get feature importance here? Let's look at it. So so let's take the absolute value of Wj, right? What is this? This is nothing but the absolute value of the weight corresponding to feature, corresponding to feature j, right? If the absolute value is large, right? If this value is large, look at it. Let's look at it diagrammatically, right? If this absolute value is large, whether it's positive or negative, that doesn't matter. If Wj is large, right, then its contribution to W transpose Xj is large. Right? Its contribution, because if let's say Wj is positive, okay, case one, if Wj is positive and large, okay, positive and large, since it is positive and large, because at the end of the day, I multiplied Wj with xqj. Remember, I multiplied Wj with xqj and I summate everything. J equals to 1 today. This is what This is nothing but W transpose XQ, right? So if Wj is positive and large, right, then it impacts my W transpose XQ also positively. And we saw that if Wj is positive, the probability of Yq equals to +1 is increases, right? So if Wj is positive and large, it impacts the probability of my query point becoming positive much higher, right? So I hope you understood that the absolute value matters. Similarly, case 2, right? If Wj is negative and large, if it's negative and large, it still impacts the Wj XQj product, right? It still impacts this heavily, but it impacts for the negative class, right? It impacts in such a way that probability of Yq equals to -1 increases, right? So whether it is positive or negative, if it is large, whether it's positive or negative, its impact in determining the class label, its impact in determining whether something is positive or negative is more, isn't it? So hence, you can tell which features are important. You can determine the important features. You can determine the important features in logistic regression by just using the absolute value of each of the feature weights, right? So now let me walk you through an example so that you understand this better. Okay, the example I'll use is, imagine if I'm given a bunch of features and I want to predict the gender given a bunch of features, right? My genders are male and female. Okay, so let me just say that male is positive label, female is negative label. You can choose it the other way around. That's perfectly all right. So when you train a model, let's assume I have some features. Let's assume I have a feature which is hair length. Imagine if I have a feature like hair length, right? So what happens is, for this feature, what would you get? This feature weight will be high, the weight corresponding to hair length. So let's call this feature HL, right? The weight corresponding to HL, the absolute weight, the absolute value will be large, because because this is very, very useful in determining whether somebody is male or female, because most women tend to have longer hair than men. That's the assumption we are making. Let's assume that's the truth. If that's the case, then hair length is very, very useful in determining whether a given data point, or whether given a bunch of features, whether the person is male or female. But remember, the weight WHL will be negative. Why will it be negative? Because I'm telling this from common sense. I'm telling this because as WHL increases, the probability that YQ equals to -1 increases, because as the hair length increases, the probability that somebody is woman, -1 is female here, right? The probability, okay, that the person is female increases. And we saw that when as weight increases, if the probability of the negative class increases, the weight itself will be a negative value. So hair length, in the real world situation, hair length will have a large negative value, or negative weight value, to be precise here, right? So something like a hair length, when you're trying to predict gender, if you have a feature like hair length, it will tend to have a large negative weight. Large because it is very useful in determining whether somebody is male or female. Negative because as hair length increases, the probability of the negative class increases, right? Similarly, imagine if you have another feature like height, right? So let's assume, statistically speaking, men tend to be, in general, taller in all populations of humans across the world. They tend to be taller than women, typically, not necessarily always, but typically from a population statistics perspective. So as height increases, the probability that YQ equals to male, +1 basically means male, right? Male also increases, which means the weight corresponding to H, the feature here is H, okay, should be positive, because as height increases, the probability of the class label being positive also increases. So it will be positive, right? But remember, height is not a phenomenal way to determine whether somebody is male or female. Because if you look at distributions of populations, you'll see female populations here, and you'll see male populations here. It's not like a, whereas hair length, right? You'll see most men having shorter hair, most women having longer hair. So much more separability. If this is your hair length, this is where your men will be. This is what your women typically will be. If this is your height, right, your women will be here, your men will be here. There is less separability between these two distributions, right? So it will get some medium weight. It will get a medium positive weight. It will get a medium positive weight, right? Because when you actually apply it to the data, that's what I mean when I say feature importance, right? And with feature importance, you also get an additional benefit in logistic regression, which is model interpretability. So let's assume okay, it's a little tongue twister here. So what does model interpretability mean? If I want to tell whether the model is sensible or not, if I want to tell somebody, in addition to saying YQ is +1 or -1, in addition to that, if I want to tell them, why am I saying that my class label given a query point, why am I saying that the class label is positive or negative? If I want to give reasoning to them, I can just pick up the most important features. And what are the most important features? Those features which have an absolute weight value, which is large. Now, for example, in this case, if somebody gives me a data point XQ, and if I say that YQ is female, then I can say, oh, I'm saying that YQ is female because this person has a very large hair length, and hair length is proportional, because as hair length increases, I know from the weight value of hair length itself, because hair length has a large negative value, I know that hair length is large hair lengths correspond to more the probability that the person is more female. So I can just give the interpretation. I can say, in addition to this, I can just look at the weights. I can look at the top weights. Top features. How do I get the top features? By looking at the absolute value of the weights, right? I can say the top features and say, oh, this person has a very large value of hair length, right? And the height is also typically shorter. And these are the two most important features to determining gender, right? So for example, if hair length is short and if height is more, I'll say yes, because lower or smaller hair length implies that it's a male, and similarly, more height typically implies it's a male. Hence, I am saying that the class label for a given query point is +1. So you can actually give reasoning. You can actually give reasoning behind your giving class labels by just using the top features. Suppose if you have 100 features. You can just pick the top 5 features or so. You can just pick the top 5 features. And how do you pick the top features? Using the absolute value of the weight vector corresponding to the feature, right? And you can easily give model interpretability. So given any query point, in addition to giving the class label, you can also say, since for the top 5 features, this query point has this type of behavior, hence we are determining it to be a positive class or negative class, right? So model interpretability is very, very easy to obtain by using simple feature importance. It's very, very simple and elegant in the case of logistic regression.